Hello, everybody. My name is Hartmut Kaiser. I'm working at Louisiana State University. The title of my talk emphasizes asynchrony. If you look at the conference website, they put the talk under concurrency. But actually, I will talk about parallelism. So I hope I don't disappoint you. If you came to hear things about mutexes and this kind of thing, you are definitely in the wrong room. What I want to do today is, or what I want to try today is to derive a couple of governing rules for writing applications so that those applications run very efficiently in parallel. And by running efficiently in parallel, I mean that if I run my application on 4 more cores than before, I want it to run 4 times faster. And if I run it on 100 more cores, I want to run it 100 times faster, and so on. I also will try to show that if you derive those governing rules or those governing principles, if you implement them in a library or in a runtime system, which can manage the parallelism for your application, and you use that runtime system to write your code, and that it's possible to do that. And if you add a asynchronous interface on top of that runtime system, which as an add-on is 100% compatible with what you know from standard C++11 or certain documents which are being pushed through standardization right now, then you end up with a way of writing code where you essentially write code very, very similar to sequential code. You take your textbook algorithm, write your code, which looks almost like your textbook algorithm, and the system will be able to parallelize that for you automatically, almost automatically. And I hope in the end that I can convince you that this is possible, so that we finally have a way to write C++ code such that you don't have to worry about concurrency issues. You don't have to worry about how to parallelize things. All you have to worry about is to get your sequential code correctly written up. And I think that is if it really is true and if it really works, and as far as I can see it worked for the applications we tried it with, that is a major step forward. And that is what I mean by the asynchronous C++ parallel programming model. And that's where asynchrony meets parallelism. OK, let's start. If you look at the landscape of today's parallelization tools we use to write parallel applications, that's mostly a set of parallel libraries, parallel facilities, like OpenMP with Pragmas or with the tasking. For distributed applications, we have MPI as a standard API to do communication in a distributed world. If you look at that landscape, you will quickly see that it's actually a pile of building blocks which are written in a way that they don't fit with each other. You can't just take OpenMP and parallelize your code and then mix that with a MPI call. I don't know if anybody has tried to invoke an MPI API call from an OpenMP thread. You would have probably failed miserably. Or you can't just take CUDA as the major toolkit for, at least for the NVIDIA GPUs, and combine that easily with OpenMP or even, well, with MPI, there's some integration there now. What I mean is that these tools have been developed for 25 years, and each of those tools has been developed independently of any other tools, and it's very, very difficult to combine those in a single application. The other thing we see, and that second image on that slide shows you what happens when you use most of the available tools today. So what you see here is a utilization graph of, I don't know, 15 or 20 CPUs. Each horizontal bar represents the utilization of one of the CPUs on a node. And the dark or the greener areas means the CPU is busy, and the light areas means that the CPU is waiting for something to happen. It can't make progress because it has to wait for other things in the system. This is a very typical expression or a very typical picture you're getting when you're looking at applications which are written with OpenMP, where you have a for loop which is parallelized, and then you have a piece of code which is not parallelized, and you have another for loop which is parallelized again, and so on and so on. So you have these very limiting join points in between the for loops, which make your application scale very badly. So let's try to find a way how we can circumvent that. I promised to derive some parallelization rules or principles from first principles. So let's start with the absolute fundamental thing when it comes to parallelization and scaling. And I promise it's the only formula I will show today. So you don't have to go back to your graduate school to understand this talk. Everybody probably has heard about Amdahl's law, right? Amdahl's law is a expression of the theoretical limit how far we can scale an application. And by scale, I mean how faster can an application run when I run it on more compute resources. And this law gives us a theoretical limit of that scalability. How much faster can an application run under the consideration of how much of your code have you actually parallelized. So in a simple case, let's say I have an application which I can parallelize to 50%. So 50% of my code is parallelized, 50% of my code is not parallelized because I wasn't able to do that. And Amdahl's law will tell you that in that case, you can't speed up your application more than a factor of 2. You can run it on 1 million of cores. It will not run faster than twice as fast than before. And that's clear, right? Because when you parallelize only half of the code, you can squeeze the execution time of that parallelized half of the code almost to 0 when you add more resources. But the other half of the application is still 50% of the runtime, right? You can't get rid of that. So Amdahl's law gives us a theoretical limit. And just to give you another example, if you parallelize 95% of your application, and that's for many applications already a very large part. Just think about initialization, I/O, synchronization, all of that, which limits parallelization. So if we are able to parallelize 95% of our code, it still can't run faster than 20 times in the sequential version. And this is a serious limitation because you can throw, I don't know, 60,000 cores at that application. It will not run faster than 20 times, and that only if you're lucky. So we are the people who are really trying to use resources in an efficient way and parallelize things in an efficient way are severely limited by the fact that they have to try to parallelize essentially everything in the application, and that is very difficult. So rule number 1 I pose is that we should try to parallelize applications as much as humanly possible. In the end, we have to parallelize it 100% if you really want to have perfect scalability. And I will get back to that, and we'll try to concretize that a bit and show you how we can actually achieve that. Unfortunately, the theoretical limit defined by Amdahl's law is not all we have to deal with. There's always the 4 horsemen, which are sitting everywhere in this world. And what I call the 4 horsemen of the apocalypse are 4 additional things, 4 additional limitations which limit scalability of our applications just from the practical standpoint, on top of what Amdahl gives us. The first of those factors is what I call starvation. Starvation means that we have not enough parallelism in our system to keep all the resources running. So half of our cores just sit there and idle because I have 16 cores, but I only have 8 things to do at the same time. So clearly 8 of the cores just idle. They don't have nothing to do. The next one is latencies. Latencies is everything what's limited by the speed of light. So the time needed to establish a network connection, the time needed to pull data out of the memory, the time needed to send data from the cores over to the GPU or back. And all these things are latency bound. So it's the time distance delay of remote resource access and services. And that severely limits our scalability because in the end it adds some kind of sequential pieces of code everywhere, spread all over the place. Overheads, those are the worst ones, the really bad guys, because overheads is something you don't have in the sense I'm talking about. Overheads is something you don't have when you run sequential code. Overheads is that time which needs to be spent in order to manage parallelism. So that's those things which you encounter only when you really add parallelism to your application. And last but not least, waiting for contention resolution. It's kind of the opposite of starvation. You might just have too much work in your system. Well, you all have been driving on the interstate, right? And there's no apparent accident or anything, but everybody's driving slow. Why? Well, because there are so many cars on the streets that everybody's driving slowly. That is contention. And the same happens in parallel applications. If you have too many things to do, then suddenly the performance goes down. False sharing is one of those factors which falls into this category. And as you can see, our 4 horsemen kind of form, if you just look at the first letters of those, you see why our applications are actually slow when you start parallelizing them. That's our 4 factors. As I already said, those impose upper bound, additional upper bound on weak and strong scaling of our applications. Okay, enough of theory. Let's look at some real-world problems which everybody probably has encountered when you were trying to parallelize things. And I already alluded to that. If you look at the programming models which people use today, OpenMP, MPI, you will see that those programming models impose additional limitations on your ability to parallelize things. Just as an example, OpenMP enforces a barrier at the end of the parallel for loop on you. There's a reduction operation, and I apologize. And everybody has to wait for A, for the slowest guy in the execution, and B, everything has to go through a single thread. So all parallelism has to kind of stop, and everything goes like through a funnel, through the sequential piece of code which comes after the loop before you again spread things out. And these pieces add additional sequential pieces of code to your execution. And again, Amdahl comes along and whacks you over the head because, well, he rejoices, right? Because there is sequential execution. You can't get the scalability you want. Other problems with those models we have today are that they tend to over-synchronize more things than required by the algorithm in order to go forward. If somebody has worked with MPI on clusters and distributed systems, you know that MPI kind of, at least in a simple case, enforces a lockstep between the nodes. So all nodes do always the same thing, then they communicate, and then they do the same thing again, then they communicate. And as long as you have only 4 or 5 of those nodes involved, that's no problem. But as soon as you have thousands of those, there will be definitely one slow guy, one node which lags behind, and everybody else has to wait for that slow guy to catch up. So something which a programming model enforces on you. And there are ways to work around these things, but these models have been written for 90% of the use cases. And the 10% of the use cases we're interested in, namely using our resources really to the fullest, is something which is perhaps doable, but very, very difficult to achieve with the existing tools we have at our hands. Also, as I already mentioned, there's insufficient coordination between on-node and off-node parallelism. There's a thing the DOE calls MPI plus X. The funny thing is that nobody actually knows what X means. So they want to combine MPI with something else to get off-node and on-node parallelism combined. But it's a grudge. And last but not least, we have distinct programming models we have to deal with for different types of parallelism. Off-node MPI, on-node OpenMP, accelerators CUDA, or OpenACC, or other things. And as I already alluded to in the beginning, those are usually not very well orchestratable, if that's a word. Somebody might say, yeah, but we have the standard algorithms in C++ now. Great. I'd say it's like with regular expressions. If you think you have a problem you can solve with regular expressions, you have two problems afterwards. Parallel algorithms are very similar. They are very simplistic, so you can quickly solve perhaps 80% of your issues. But when you really want to control parallelism and really want to do utilization, increase utilization of resources, parallel algorithms will limit you. And mostly because they are, well, fork join again, right? You have to fork many threads and you have to join them at the end of the loop before you can continue. And that picture kind of depicts that, right? Instead of running things sequentially, you kind of spread them out. Then you have a piece of sequential code. Then you spread things out again. Then you join them. Then you spread out again, and so on. And those sequential pieces is what's killing your scalability of your application, believe it or not. Another example which demonstrates that, in this example, in this image, time goes down from top to bottom. And you can see that things are spread out. Then many threads work on the tasks in a parallel loop or in a fork join region. Then you might have a reduction operation where you have to wait for the slowest guy. Half of the cores are already done, and they wait. And one of the cores just takes a little bit longer than everybody else, all the other cores. So all the other cores have to wait for that slowest guy before you continue. Again, it adds these sequential pieces of execution which are so bad for scalability. So my rule number 2 is try to use a programming environment that doesn't fight slow, but that embraces slow. And by that I mean, for instance, how do you embrace starvation? Well, I already said in rule 1, let's parallelize as many things as I can. And if I have many things parallelized and a large amount of work in the system, then I can avoid starvation because I always have more tasks pending to be executed than I have resources at my disposal, which is good. How can we embrace latencies? Well, latencies, what you need to do, you need to utilize the inherent parallelism available in the hardware, right? You can do things on the GPU at the same time as on the cores. Has anybody tried using CUDA and still do things on a CPU while the GPU is churning your numbers? Some people have done it. It is definitely possible, but sorry for my French, it's a pain in the neck, right? So nobody is doing it in the end because it's so difficult to achieve. I'm not saying it's impossible. I'm just saying that the mere mortal programmer has a big problem when it comes to that. So if we have a program model which allows us to easily overlap the work on the GPU with the work on the CPU, or to overlap the ongoing network communication which was useful work on a CPU, or even create hardware which allows us to overlap memory access latencies, then we get a programming model which is much more suited for parallelization. Overheads I will mention specifically on the next slides. And you might say, how do I get rid of that waiting for contention? Well, one of the reasons for the contention or for the waiting we are seeing is that the programming models tend to force you to synchronize on more things than you actually need to go to the next step. Very often you have a parallel for loop, and you could already start with a code afterwards for the first iterations which have already finished executing, while the other iterations are still ongoing. But no, the program models enforce that you have to wait for everybody to finish before you can go to the next step. So if you find a program model which allows us to express fine-grained synchronization by making sure that as soon as all preconditions for a particular computation have been met, I can go ahead with that computation, then we can get rid of a lot of contention because you kind of distribute the contention over time. So you don't pack them in the same amount of, or same spot of time, but you have a lot of things which go on, which are very nicely distributed. And that helps with mitigating those factors. Okay, let's do a thought experiment. Let's assume we have 10 million tasks. And each of those 10 million tasks takes 100 nanoseconds of time. So overall, it's 1 second of work. And let's assume I have a system which allows me for these tasks to run in different ways. I can either run all the 10 million tasks on one thread, so I get essentially sequential execution, or I can run these 10 million tasks each on a separate thread. And then we try to analyze what is the runtime I'm getting out of that. So what this yellow curve gives you is essentially the runtime when you vary the amount of tasks run on a single thread. On the left-hand side, you have the case, you have a grain size of 1. That means you run 1 task per thread. And since threads impose overheads, as we all know, your execution time will go through the roof because that yellow line assumes that you have 1 microsecond of overhead per thread. So the runtime for one task is not 100 nanoseconds anymore, but 1.1 microseconds. So if you add that up, you get, I don't know, 10 seconds of execution time where 90% is, or 99% is just overheads. On the other hand, on the right-hand side, you see the case when you run everything on a single thread. And you might wonder why it's still a bit slower than the sequential execution. And this is an artifact of effects of contention and false sharing in the scheduler. And you see that very quickly when you decrease the grain size from 10 million down, you very quickly gain speed up. And that's what you normally would expect, right? When you parallelize a for loop, what is your kind of the first intuition you have? Well, I know I have a certain amount of work, so let's split it up equally for all cores I have. Let's say I have 10 cores, so each core gets 1/10 of the work. And that's a common way of how people do parallelization. But as you can see, that doesn't give you the best possible performance. The best possible performance is here when you run around 10,000 threads with, I don't know, 10,000, probably 10,000 tasks each. Things get even worse when you increase the overheads. This is a theoretical model, right? It's really just a crude qualitative modeling of what's going on in a system. The blue line gives you the resulting execution time if you have 100 microsecond overhead per thread. And you see you are severely limited already in terms of what you can achieve in speed up. And if you get just say, hey, one thread has 10 millisecond overhead, you essentially are dead in the water. And if you think about it, 10 milliseconds overhead is essentially what you get when you use a pthread, because you have operating system time slicing, which in the best case gives you 10 millisecond latencies or overheads for a single thread. And in that case, you can't even get to the optimum anymore, not even close. So for even relatively small amounts of work, we can benefit from split into that work into smaller tasks. That's what we learn here. And you will end up with a possibly huge amount of threads, 10,000 in that case. And the best possible scaling we predicted here would be reached when we use 10,000 threads for 1 second of work. Isn't that amazing? That just tells us that there's possibly so much parallelism in our applications, and we can split them up in very small tasks, that we really can create enough work to keep every compute resource we have in our system busy all the time. Okay, it's a bit theoretical because there are no synchronization, no dependencies, anything, but you get the picture. But there are several problems, right? It's impossible to work with that many kernel threads, P threads, obviously. It's impossible to reason about 10,000 threads at the time. I can't reason about 2 threads at the time. My wife can probably. She claims at least she can, but I can't. So how do we deal with that? Again, we need a higher level programming model which allows us to reason about the code, even if it's underneath using a humongous amounts of threads, billions of threads. So rule number 3 is allow for your grain size to be variable. Write algorithms in a way which allow you to modify the grain size of the algorithm at runtime, because that will allow us to do adaptivity at runtime and to decide at runtime how much of work you actually want to execute on a single thread to get best possible performance. This is a graph. The previous graphs were theoretical. This is a measured graph from a 1D Stencil application, very simple application, which just computes heat diffusion on a 1D ring. But still, if you modify the grain size in that algorithm, namely the number of data points you calculate on a single thread, you get that very same dependency. But what's so beautiful of this graph is that you see that the minimum is actually very close to the left edge and not on the right-hand side. And that's very symptomatic, and we see that essentially for any applications we analyzed. So what you want to do, you want to make your tasks or your threads as small and short-lived as possible, but not shorter. Because if you make them too short, bang, you hit the wall and things go up in a very steep curve and your performance goes down the drain. This is a result only a few people think about, because mostly you are kind of on the right edge of the things, right? All these graphs are kind of done for 16 cores. So if you divide the 100 million or whatever that big number is by 16, you would get to the point where you get that equally splitting of tasks for cores I was mentioning. But we have to go far, far to the left, and note the x-axis is logarithmic. So there is a lot of room where we can decrease the amount of work on a single thread. On the other hand, as you have seen in the previous slide, it's absolutely crucial that you have a system which gives you minimal overheads for the thread creation. Otherwise, you're dead in the water as well. So rule number 4, oversubscribe. Create more work than you can possibly handle with the resources you have, because that gives you always enough work for the resources to work on, so that avoids starvation, and build balancing of your and balance adaptively. Build your system in a way that you can control the grain size or other aspects of your system at runtime. So what challenges do we have? And I need to speed up a bit. So I might start skimming a bit over it. Otherwise, we will not get to the results today. We need to find a usable way to fully parallelize applications. I said that already. We need to expose asynchrony, and that's what I propose here. Expose asynchrony to the programmer without exposing additional concurrency. Because if you have 10,000 threads, you don't want to deal with 10,000 threads on a single mutex or this kind of thing. So you want to have a programming model which kind of encourages you to write code which is data race free by definition. Value semantics, functional style programming, and so on and so on. And if you have such a programming model, then you can deal with billions of threads without even, okay, I have a bit of gray hair because of that, but normally you can just write code as if you were writing sequential code, and I will give you an example. The other important thing is that you have to make data dependencies explicit. The goal, remember, in the beginning was to write sequential code, but still have the system parallelize things for you. How can a system parallelize things if you don't tell the system which things have to run in what order? What depends on what? So you have to tell the system somehow what are the dependencies for the next step? What does it has to wait for in order before it can make progress? And I will show you how you can make these data dependencies explicit in an easy way. Well, obviously, we want to provide manageable paradigms for parallelism. If you deal with 10,000 threads, you might say, that's what I get, right? But I really hope to convince you that there is a way out and that we can avoid these situations. Proposed solution, asynchronous programming models. We want for objects to interact through asynchronous function calls. Remote calls, by the way, can be done as active messages and can be integrated so that you end up with a system where remote operation is completely semantically equivalent to local operation. And not only in tightly coupled systems like clusters, but in things like distributed applications, service-oriented applications on modern clouds. Same thing, same principles apply. What we will do, we will use futures to represent those data dependencies. And I will show you that essentially what we have in C++11 plus some extensions from the concurrency TS are completely sufficient to achieve all those goals I was mentioning. We want to look at the entire machine as a single abstract machine. That's more for the people who are interested in distributed computing. So we want to have a global address space where all the nodes kind of work with the same addresses. And tasks operate on C++ objects in a distributed system. But that's kind of just the general guidelines. I mentioned it, semantic and syntactic equivalence of local and remote operation is important for us, at least for us on the HPC environment. I will present a futurization technique which achieves all of that and tries to overcome these problems I was mentioning. And we want to be fully conforming to the C++ standard API, so that you can just go in and jump in, even if you don't know anything about HPC or about parallelism. But you know C++11. You can start right away and work with that and write highly efficient, scalable parallel code. Okay, what is the future of computation? I talked about the universal answer on other talks. I thought that slide is nice. I can bring that back. Everybody knows that the universal answer to life, universe, and everything else is 42. The problem is that calculating that answer takes 7.5 million years. Literature tells us that. So what do? We construct a computer which is called deep thought. And the first thing we do, we asynchronously launch the function which will give you eventually the universal answer. I use the C++11 async here, which launches a new thread, which runs the function. And that gives you back a future object, a future of int in that case, which is a promise that the answer will be delivered eventually. It represents a result which has not been computed yet. Then we do something else for 7.5 million years because we don't want to wait for it to happen. And when we come back, we say, OK, now I want to have the answer. Give me the answer. Yeah, I want to see it. I have waited long enough. So I call get on my future, and two things can happen. Either the function has returned the value, and the future will give you the value and will say, yeah, here, go away. Here's the answer. Or it might, if the answer has not been computed yet, the future will suspend inside get and will come back out of get only once the answer has been delivered. It's a beautiful model to decouple producer-consumers. You don't see any notion of thread, nothing. You don't even see any notion of synchronization. It's just a beautiful way to make asynchrony available to the user. And the good thing is, essentially, a future represents a data dependency. Because the data dependency means whenever that future becomes ready and the value is available, I can continue with my computations because now I know that the answer is actually 42, which I didn't know before. Well, you might have known it, but. So what a future gives us is a transparent synchronization with a producer, which is nice. It hides the notion of dealing with threads, which is absolutely crucial when you're dealing with tens of thousands of threads. It makes asynchrony manageable. Well, every beginner C++ programmer can write that code and calculate the universal answer. It allows for composition of several asynchronous operations, and I will show you how that works. And the beautiful thing is it actually turns concurrency into parallelism. It's not doing that literally, but it encourages a programming style which, when you follow it, will avoid any data races. This is the good part. Okay, let's look at some example. And I just thought, let's look at recursive parallelism, because that is a problem even in OpenMP, right? You have to be very careful not to have nested for loops and this kind of thing. So recursion in OpenMP is a problem. Okay, with the tasking API OpenMP gives you, it might be possible. But recursive parallelism is always an interesting problem to look at. And no, I will not use Fibonacci number calculation to show you what I mean. I just want to traverse a recursive tree. Let's say I have an octree. An octree is a tree where a node either has no children at all or it has 8 children. And it just goes down. And different ends of the tree might have different number of different depths, so it's not balanced also. How do you do that? Well, that simple traverse function, in the simplest case, we are at the leaf, so all we have to do, we have to compute the result for the leaf. So let's say our compute result just counts a number, or we want to return just the number of nodes we have in our tree. So in that case, the compute result will just return 1 because it's the leaf node, so the leaf node counts as 1. If I have children, what I do, I just create an array of 8 values, and I recurse into all the children of that tree and collect all the results. And once I have those, I combine the results and return the overall answer for that particular node. Very simple traversal of an octree. Now the question is, how do I parallelize that? Well, in the simplest case, just let's apply what we learned from the universal answer. If everything's okay, if we are at the leaf, we just have to compute the result, same thing as before. If we have children, what we do, instead of collecting the actual result, we collect the futures representing the result for each traversal into one of the children of my current node. And I spawn a new thread. Let's assume those threads have no overheads at this point, just to get the semantics clear. So I launch 8 new threads. Each of the threads traverses into one of the children of my current node. And I collect the futures in my result array. Then I kick off my local computation because I want to overlap the local computation with the ongoing work on the 8 children. And once I have my local computation done, I wait for all the futures to become ready with the wait all function. And then I combine the results as before. Easy. And you might say, hey, great, I parallelized my traversal. Well, you did, but you didn't. Because what you did here is introduce fork-join parallelism on each level, right? You spawn it off, you wait for them. You spawn it off, you wait for them. And that's exactly what you would do when you use OpenMP tasks, for instance. Because OpenMP tasks are not allowed to leave the current context they are created in. So you have to wait for the task to finish before you can exit that function which created the task. Fork-join parallelism over and over again. And that adds these nice contention points all over your iteration, which makes that thing, well, slow as hell. So what can we do? Well, there's a very simple technique, and that's what I call the Futurization technique, and we will see that over and over again, is what if traverse actually returns a future itself? And now things get interesting. So traverse returns a future itself. What we do now, and let's assume compute result returns a future representing the computation for that child node. If you have children, then we launch threads again with async, but this time we collect the futures and don't wait for them, but we pass our futures to a function which here for simplicity is called when_all. And when_all is essentially taken from the concurrency TS, which is discussed in the standardization. And when_all does the following. It takes a bunch of futures and gives you another future which will become ready when all of the input futures have become ready. Right? No computation happens. It's really just I will become ready when all of my arguments have become ready. And still nothing is being computed. It's really just the dependency which is defined. And when_all gives us a future, and then I do .then on the future return from when_all. And .then means, please call the function I give you whenever you become ready. So the .then takes a lambda, and the lambda is being called with whatever the arguments of when all have been. And the lambda is called when all the input futures, the results array, and whatever tcompute result has returned have become ready. So inside that lambda, I know that all the futures have become ready, and now I call combine results. And the beautiful thing is that the lambda returns a value, and that value comes out packaged in a future from .then. So .then gives you a future representing the result of the computation which is attached to the future. Sounds a bit complex. It's the future all over the place, but hey, we want to solve the problems of the future, so this is only appropriate. If you think about it, what have we done? This function doesn't compute anything anymore. It gives you a future representing the result it will eventually compute. So the future return from that function is representing a dependency tree of other futures. Because the future return from the function will become ready when all the input futures have become ready. And those become ready when all the input futures of those have become ready, and so on and so on. So the topmost traverse function gives you a future which kind of will become ready when all of the tree has been traversed. So what we have done, we have turned our initial function into a function, the initial function was computing things. But now we have a function which doesn't compute things, but which gives us an execution tree, a dependency tree, which, when unraveled, will give you the result. So it's kind of monadic transformation. I don't want to talk about monads, but it's a monad, believe me. So what we did, we created a compiler which will, at runtime, generate a dependency tree which corresponds in structure to my algorithm I executed. And that's so beautiful because the dependency tree can be executed in full speed because there are no synchronization points. Everything happens asynchronously in that execution tree. When the lowermost futures become ready, they just propagate through the tree, and those attached continuations are called on each level, and eventually the outermost future becomes ready. So we get rid of all the synchronization. No mutex, nothing. But we still get the same result. And you might say, hey, I don't want to write this nasty code with when all. I understand you, I hear you. Luckily, there is something like a coroutines proposal currently. Is it a TS already or not? I don't remember. It is a TS now. And that coroutines proposal has a facility which is called co-await. And co-await is a very flexible tool which can be extended in all directions by your facilities. And if you use co-await on a future, it will do the same transformation under the hood as we have done explicitly. So if we use the co-await representation, look what we get. I essentially just inserted co-await in front of all the futures, and in the end a co-return, because they decided that those functions can't have a return statement. They have to have a co-return statement. OK, let's call it co-return. And now this code looks essentially like our initial sequential code of traversal, right? Do you remember that? So all what's changed is that instead of calling the traverse of the children directory, I now use async. And instead of having nothing, I put a co-await in front of where the futures are. That's the only transformation I do. And that's what I mean. We write code which looks essentially almost like sequential code, but which is fully parallelized and runs as fast as it can and on as many resources as you have available on your system without you doing anything. OK, let's go on. Sometimes, or very often in your systems, you don't have just one function you want to parallelize, but you have to communicate, either across nodes, between NUMA domains, between the GPU and the CPU. There's a lot of communication going on. And what we were implementing, what we were playing with, was to build an asynchronous communication mechanism, which kind of plays very well with that future asynchrony model I was referring to. What we did was just looked at Go. Go has, some of you probably know Go, that language, Google Go language. And Go has a language built-in facility. You have 15 minutes left. Okay, so I have to really speed up because I'm not even half through the slides. Thank you. And those Go has channels, and channels allow to do a kind of a pipeline between 2 points in your application, where you can send data in on one end and get data out on the other end. But what we did, we made them asynchronous, just by having a channel which has two functions, a get and a set, and both give you a future representing the operation they're working on. A simple, quick example. Let's assume we have a 2D problem where we split up our computational space into 2D batches of data points, where each of the data points could be distributed in a system on different NUMA domains, on different localities across the system. But we still have to communicate between those. And the thing is here that each of those computations are done cyclically, time-step-wise. So you do some computation, then you have to exchange the boundary nodes in order to propagate the information into the neighboring computational domain, and then you can continue on the next time step for diffusion problems or for all kind of scientific computing problems. So those vertical and horizontal bars are the communication buffers, and the arrows represent channels. What normally happens in high-performance computing is that you do that with MPI, and all of those computational domains always have to be on the same time step. They do computation, then they communicate, then they do computation, then they communicate, and so on and so on. So they have that flip mode back and forth between communication and computation, which keeps everybody nicely on the same time step, which kills our performance. So on that image, the patch C is not done with the computation, but A, B, and D are done. So B and D and A can already start communicating their boundaries to their neighbors through channels. Now, B is the only one which can continue because the others have to wait for their communication to come in, right? But B can go ahead because all the communication, all the boundary exchanges have been performed in order for B to continue. So B goes on the next time step. And eventually B is done and sends its data back to the neighbors. The point of this image is just to show you that you can nicely use channels to decouple computation in the system, and you can let go every piece of the computation ahead as far as possible without having to wait for everybody else who might lag behind because of some, I don't know, thermal problem in the node, or phase of moon is wrong, or something else is going on the network in the system which keeps back that node, and so on. Okay, so let's do Asynchrony Everywhere now, and we are coming along quite nicely. What I want to show you is such a 2D stencil application which does essentially what I just depicted in code, and how that can be made asynchronous. Well, you have a time step loop for a certain number of steps, but instead of having just a loop, what we do, we create a future which represents the computation on one time step. And then we use that future and attach, whenever it becomes ready, and a continuation is executed, which does the next time step computation. And whatever that dot then returns, we assign to the initial future and repeat. So essentially, that gives us a linear dependency of all time step operations in a very asynchronous way, right? Well, what's left is you have to perform one time step, right? So instead of having the loop, which directly calls one time step, we've wrapped that into that continuation-based model. And we could do the very same thing with co-await, but I'll leave it at the future on that level because it's kind of a bit more understandable. Now let's have a look at the perform one time step function, which is inside that loop. Well, what we start off with, we have 4 channel objects in all 4 directions, 4 incoming ones and 4 outgoing ones, right? In each direction, 1 channel object, as depicted. First of all, we have to wait for the data from the upper neighbor to come in. It gives us a future, so that is the top boundary future. Once that top boundary future becomes ready, that continuation will be executed. So we attach a lambda to that whenever the data comes in from the top neighbor, we execute that function. Well, in that function, we just do the boring math. We do our ghost zone. We just handle the first row of our patch. And once that's done, we send back the result to our upper neighbor, because that's what all we have to do there. So there's a channel up to and the channel up from, which do the communication in that direction. We do the same thing for all 4 sides of our patch. I'll just show one code. Then we want to apply the stencil to the partition, right? We want to actually do the operation on the rest of the patch besides the boundary nodes. Well, that is probably just a parallel for loop, which is going over all the points in our patch and doing some computation. The trick here is that we made that parallel for loop asynchronous. That is kind of the C++17 parallel for loop. And except that instead of the first argument being par, which means run in parallel, the first argument is par task. And in our case, that means run that algorithm asynchronously and give me a future representing the execution of that parallel algorithm. And now I have 5 futures, 4 from the boundary exchange and 1 from the central computation, and I pass all of them to van all, and the result I give back to my caller. Bam. That's exactly the same principle as I applied for the traversal, just for a fairly complex operation on a time-step-based stencil, 2D stencil code with full communication, and you don't care whether the communication goes over the wire to the neighboring node. Everything is asynchronous. And in the end, you get the same thing. You get a dependency tree, which when unraveled with full speed, without any synchronization, gives you best possible performance in your application. And this technique of transforming a straight code into asynchronous code is what I call Futurization. So it's a technique which allows to automatically transform code, delay direct execution in order to avoid synchronization, turn straight code into Futurized code. Code is no longer calculated directly, but generates an execution tree which will calculate when unraveled. And the execution of the tree is performed with maximum speed because no synchronization is happening. It only depends on the dependencies, on nothing else. So that's a simple scheme how you do the transformation from straight code to Futurized code. One remark, when you async a function which already returns a future, async will return a future to a future, and it has been shown that it's possible to unwrap that. You don't need the outer one, you just need the inner one. So the lower right rule can be simplified to do nothing with asyncs, because in both cases you get a future back. All that is nice and dandy. You say, okay, that's cool, but how do I do that in real code? I have to write all that stuff. No, you don't. There's a library, and that's what I was mentioning in the beginning. Thank you. I will make it in 5 minutes, I promise. There's a library which already does all of that magic for you. And it exposes a C++ API, which is conforming fully to the C++11 standard and with certain extensions which are aligned with its standardization as well. And that library is called HPX, and I will just mention it very shortly here. It's a general purpose parallelization framework, runtime system you can use in your code, which gives you the standard library for concurrency and parallelism, essentially all parallelism things you would wish of for your application to have today. Very flexible parallel algorithms. By the way, it's the only library which implements all of C++17 parallel algorithms. They are not available anywhere else in a conforming way. It enables write fully asynchronous code, which hundreds of millions of threads. And the example I will show in the end, there we were running hundreds of billions of threads on a very large machine with that library, so it works very nicely. And it gives you the unified syntax for local and remote operations. Let's skip that. That's marketing speech. You can read up later on that. The important part is it's open source under the Boost license, so you don't even have to tell us when you want to use it. We have a large amount of users, about 100 contributors worldwide. So it's a fairly large open source project. Okay, one example. and then I'll shut up. This is one snapshot of the simulation of two white dwarfs, a binary star system with two white dwarfs. That's special small stars, which tend, when they start coalescing, get closer and closer and closer. In the end, they blow up as a supernova. And that's very interesting for us physicists. And this is just showing you one of those visualization of one of those kind of snapshots. On the left is a more compact star than on the right. It's much smaller than the right star. The left star is about 5 times heavier than the right one. And you can see that those stars are so close together that the heavier star starts pulling matter from the larger star over in that accretion disk. So that this is that stream which you see forming there. And this is what's very interesting to our physicists. I'm not a physicist. They claim this is just what they want to see. So they're very happy with that. Implemented as that was a octree, non-surprisingly. So you can see that things are being refined adaptively where the actual action happens. So you want to go down up to, I don't know, 12, 14 refinement levels in order to get the precision you want in the area where the physics is happening. And in the rest of the space, nothing is happening anyway, so you don't need any resolution. Yeah, this gives you a video of what we produced recently. That is the same simulation, just showing you some time steps, essentially the evolution of those two stars. And as you can see, the closer those get, the more violent gets the process, and in the end, the one star gets sucked up by the other one, and things blow up or not. So that is exactly what our physicists like to see. The different colors are density iso surfaces. Each of those is 1 magnitude apart. So you see 10 to the 5th in ratio of magnitudes between density magnitudes in space. Okay, some graphs. This is an application, as I said, we ran on a KNL. It's an Intel modern architecture. KNL stands for Knights Landing architecture. That's one node has 70 x86 cores, and each of those cores can run 4 hyperthreads at the same time. So essentially, one node gives you 280 hardware threads. This graph shows you the scaling on a single KNL node when 1, 2, and 4 hyperthreads are being used for that particular application. And for one hyperthread, that orange line gives you the parallel efficiency. So that essentially means scaling out on one KNL node from 1 to 70 cores gives us a parallel efficiency of about 95% or so. So fairly good. So we sped up almost 60 times when we were scaling out from 1 to 60 cores. The next graph gives you the scaling for the same application without changes on the full system. The full system in that case were 10,000 nodes of those KNLs. So you see the graph for about 650,000 cores. That graph is split into pieces because you can't just run the big problem on the small number of nodes, and you can't run the small problem on the big number of nodes because there's not enough parallelism in there. So we had to split that into different chunks, and each of those lines gives you 1 refinement level. So 1 more level of refinement added to the problem, which increases the problem naturally. And on the left-hand side, you have 10 levels of refinement, and the very right-hand curve gives you 14 levels of refinement. And as you can see, the whole thing scales very nicely. For that full system run, we had a parallel efficiency of about 25% compared to 1 core. So scaling from 1 core to 650,000 cores, we still get a parallel efficiency of 25%. And I think that was fairly good result. And by the way, we got awarded from NERSC where that machine is running. And by the way, thank you so much for NERSC giving us the time. I think we burned 30 million CPU hours on that machine just to do this run. Thank you so much. And they awarded us for that result. So we are very proud that we achieved that. I'm done very quickly, I showed you that image in the beginning. When you apply those techniques, you get this. Suddenly, everything runs very nicely. You don't have these characteristic stripes anymore. And if you look at those building blocks, you get actually this, because everything fits nicely together. Everything is built around that one single thing. Session is over, and I'm done. That's almost my last slide. Thank you. Everything is surrounded one single principle, namely using futures to represent data dependencies. So everything fits very nicely together. Okay, thank you so much.
Well, so for this to work, the futures have to be extremely lightweight, right? So you don't have any synchronization primitives inside of them, or how does that work?
I'll come down because is the mic still on? Yeah, okay. HPX uses a user-level threading system where the overheads, a user-level threading system, where the overheads are very small. So the overheads for a single thread are sub-microsecond. Create, schedule, run, delete, 800 nanoseconds or so. And the future, well, it's essentially just one allocation and some minor synchronization in there. But it's very, very lightweight. One heap allocation, yes. Well, you have to allocate the shared state in the future.
I really like the 2D stencil example. But I'm not convinced that it scales better than the fork join model because you show 2 timestamps in the slides. But let's say that C, which I believe was the slow tile, let's say that there is something special about that tile and it's always slow. Isn't that going to bound essentially the progression of the whole algorithm?
No. You have enough work in the system to keep everybody busy.
But the other ones cannot continue more than one time step unless...
You can continue as much time steps as wide as your system is in terms of patches.
Right, right. So in this case would be still like just one time step ahead.
Well, on that small figure, yes, but normally you have tens of thousands of those patches, so you can have a fairly large difference between the time steps. And once you're done on one end with your computation, you can redistribute things so that everybody else is helping with the rest of the computation, and that gives you the speed up.
And that is the second part of my question. Like you didn't mention anything about load balancing. Like
right.
In this case, like what would be how would you do load balancing with this approach?
Well, locally on a node, you do load balancing through work stealing.
Right.
And in a distributed system, you do load balancing either by regenerating the tree and redistributing things, or dynamically moving things around in a system, which is why we have that global address space. So HPX gives you a global address space spanning all the nodes, so you can move things from one node to another without the application even knowing. And right, so load balancing is done that way.
So that would fall under overhead, right?
Yeah, but it's nicely overlapped because the cores have all the cores are busy. You're not wasting time. The overheads are not on the critical path, but the overheads are kind of hidden behind useful work because you have so much things to do in your system that nobody is waiting for anything.
But don't you have to rebuild the graph, the dependency graph?
Well, if you just move one node over, you don't have to rebuild any graph.
Right, but that's not changing the graph. But if you have to like regenerate the graph, that's the first thing you mentioned in terms of load balancing.
That's two possibilities. If you have to rebuild the graph, you certainly add some limitation in there. But here we were doing things dynamically. So we were moving the boundary nodes over to, or the boundary patches over to other nodes dynamically in the background. And that worked very nicely, as you can see. So,
thank you.
Please.
Hello. I have two quick questions. The first one is we have an implementation of something like your futures at work. One question that so often come again is there a situation in one of the algorithms or in .zen of future where you should implement an automatic unwrap?
We have not implemented an automatic unwrap.
We think
what we have done, we created a special unwrapping constructor for futures.
Oh, the function that takes several futures?
The function which well, you can construct a single future from a future to a future, and that the unwrapping is happening there.
And the second question is, did you look at the recently published concurrency library from Sean Parent, which have some differences with yours? And
yes,
what do you think about it?
I have looked at that, not too closely, but I have seen it. And Sean has developed his library after he has looked at what we have done. I talked with him for a while about that. So our goal was really to be very conforming to what the C++ standardization committee is doing. And Sean was free of that restriction. So he created something which might be better API-wise. But what we have seen is that even the stuff, as limited as it might be, which is currently being discussed in the standardization, is sufficient to build such a system. And that was kind of the goal, what we wanted to show.
Thank you.
Hi. I would like to ask your experience with GPU cards. Like,
yes.
I know like there is dynamic parallelism, and but the granularity in here is per core and per thread. I think for GPU cards, they are not such granular. And what was your experience?
Well, for the GPU, what we do there, we launch the kernels on the GPU,
yes,
but expose the execution on the GPU through a future on the CPU side.
Okay.
So that that future becomes ready whenever the GPU is done with that particular kernel. And that allows us nicely to continue working on the CPU side and synchronize with the work on the GPU and doing transparent data removal and all that in a very consistent way, which very nicely integrates with the rest of it.
I see. So, yeah.
We'll take the question offline if you wouldn't mind.
Okay.
We can continue discussing that. Okay?